No.
Yeah, we have a couple minutes, but maybe we can start just about 2 minutes before the time. So yeah, it's really nice to be here. It's my first time in ISI. Very nice photo of Mahalanobis, and very nice usual picture on Somnath's slide. So our first speaker is Somnath Bharadwaj, and he will give us a review of 21 centimeter cosmology. Somnath, whenever you want to start.
So, can you hear me at the back? Yeah. So, let me thank you, the organizers, for giving me this opportunity to speak here. And I have been asked to speak on this topic, cosmology with the 21 centimeter line, and I have been asked to give a brief review. So, I will try to keep it brief, focusing on the word brief. Okay. And let me give some background in case there are some people who are not working on this, but who are present in the audience, because this is a statistical institute. Maybe there are some statisticians who are attending this talk, or people with interest. So, so we are working in the context of the expanding universe, and if you think of the universe as filled, can you, yeah, as filled with a mesh like this, a grid like this, at some time in the past, then in the future, at present, this same part of the universe would have expanded into this. And you can imagine the whole universe being filled with a mesh like this. And the important consequence of this is that if there is a source here emitting radiation, and there is an observer here who receives the radiation later on, then the wavelength of light, if the light is emitted at a wavelength lambda emitted, when it is received by the observer at some later time, the universe would have expanded, and the wavelength would have increased by a factor 1 plus z, which is the redshift. Okay. And so this is the same thing. An observer here looks out and receives light from different parts of the universe. The light will be redshifted, that is, the wavelength of the light would have increased by the time it reaches the observer. And the further away the light comes from, the larger is the increase in the wavelength. This thing has. Can you see the light of the laser? The laser, it is okay. So the further away the light comes from, the more is the redshift, that is, the larger the change in the wavelength. And another thing is that the further the light comes from, the further back in the past that we are seeing. So the redshift is a proxy for two things. One is the distance, and other is the time. So larger the redshift, the further back in the past that we are looking. Okay, so two things we have to bear in mind. And this 21 centimeter line that we are talking about, it originates from this particular transition in neutral hydrogen H1. And what happens is that the hydrogen in the ground state has an electron and a proton, both of which have spins. And if there is a spin flip, there is a transition. So this transition has an energy associated with it, and that energy corresponds to a frequency of 1420 megahertz or 21 centimeters. And this is the radiation, the line that we are talking about. So this transition occurs in neutral hydrogen, which we denote by H1. And if the hydrogen is located far away, we will see it redshifted. So the wavelength would be larger and the frequency would be smaller. Okay. This pointer has stopped working. It is changing, but no, one second. Okay, let's see. The laser works sometimes, and I think the battery is LCD. Okay. And why hydrogen? Well, if you look at the constituents of the universe, what we believe now, 75% of the universe is dark energy, something which we don't know what it is. And Of the remaining 70%, remaining 30%, roughly 26% is dark matter. Again, we don't know what it is. 4% is baryons, that is the protons and neutrons which we see around us. Of this baryon, 75% by weight is in hydrogen and 25% in helium. So hydrogen is the most abundant known substance, the known constituent of the universe, which is why we are so interested in hydrogen. Okay. Let me also introduce this, the cosmic microwave background radiation. So this is a radiation which we know fills the entire universe. You take a radiometer and point it in different directions, you will see the same radiation coming, and the spectrum of this radiation has been measured, and it is found to be a black body to a high level of precision with a temperature of 2.73 Kelvin, and this radiation is nearly isotropic. This is the most precise black body radiation that has ever been measured till date. And this radiation which we receive here, we believe fills the entire universe. And if you go back in the past, this radiation, the temperature of this radiation, which is 2.73 Kelvin at present, if you go back in the past, past means higher redshift, further away, the radiation, the temperature of this radiation increases as 1 plus Z. And by a redshift of 1000, the radiation has a temperature of around 3000 Kelvin, sufficiently hot to have ionized whatever hydrogen there is in the universe. And once the universe is ionized, it becomes opaque, the radiation cannot propagate freely, there is Thomson scattering. So, sitting here, we are receiving this radiation from a shell at a redshift of 1000. Okay. Before that, the universe was opaque and this radiation was getting scattered. And we are seeing this surface as the cosmic microwave background. What we see now actually maps out this surface. And this is a picture of this surface. So you can see that the radiation is nearly isotropic. There are tiny fluctuations of the order of tens of microkelvin, which WMAP and Planck have mapped out. So this is a picture of what WMAP has measured, and there are tiny fluctuations of the order of 10 microkelvin there. Okay. Thank you. So now, yeah. Okay. So the universe is also filled with this radiation. Not only is the universe filled with hydrogen, it is also filled with this radiation, whose temperature now is 2.73 Kelvin, and if you go back in the past to higher redshifts, then the temperature of this radiation gets higher and higher. Okay. So now let me introduce this picture, which I think is familiar to many of you who have attended my previous talks. Okay. So this picture, I trace out the evolution of the neutral hydrogen. Not only that, I also use this to explain what we hope to see. Okay. So in this picture, the observer is here at the origin and the observer is looking out. Okay. Looking out in this direction. And as you go further and further away, it corresponds to a higher redshift. Okay. So this is a redshift of 630,000. And if there is hydrogen here, then if the observer here receives the radiation from this hydrogen, if the hydrogen is located just at the position of the observer, it will be at a frequency of 1420. But if the hydrogen is located far away, say at a redshift of 30, then the frequency at which the observer will receive this radiation will be redshifted like this, and it will appear to this observer at 50 megahertz. Okay. And a redshift of 6 around 250 megahertz, etc. Okay. So this frequency is the frequency at which the observer sitting here, that is, will receive the radiation, 21 centimeter radiation, which is emitted at 1420 megahertz by a distant hydrogen atom. Okay. So the higher the redshift, the lower the frequency and the further out we are looking. Okay. Before a redshift of 1000, the universe was ionized. So, the CMBR photons which we are seeing here now, they were not able to move any significant distance. They were constantly being scattered by Thomson scattering in the ionized medium. The electrons scattered the photons. So, the photons here cannot move freely and they keep on getting scattered. At a redshift of 1000, the universe first becomes neutral, the hydrogen first becomes neutral. And once the hydrogen is neutral, these photons can propagate more or less freely. So, they propagate freely and we receive these photons here. Okay. So, this is the basic picture. So, if you look out at a redshift of 1000 far away from here, the universe, you will find that the universe was ionized and you are receiving these photons from that surface, the CMBR. Now, the point is, as the CMBR propagates from here to the observer sitting here, it has to propagate through this hydrogen. And this hydrogen will imprint the CMBR photons as they propagate to this last scattering surface to the present. And this is what we are interested in. Okay. So now, the question is, what happens to these photons? What happens to these photons, the CMBR, the cosmic microwave background radiation, which fills the universe as they propagate from this last scattering surface to the observer here, from a redshift of 1000 to the present. What happens to these photons as they propagate? Okay, they are in through this hydrogen, through this universe filled with hydrogen, neutral hydrogen. That is the question. Okay. And to understand this, let us now look at the hydrogen. Okay. See, the hydrogen has two states as far as we are concerned. There is the excited state of this hyperfine transition and there is a de-excited state of the hyperfine transition, which are separated by a energy which corresponds to 1420 megahertz. So, you can express the number density of atoms in this state and the number of density of atoms in this state, the ratio of these two through this Boltzmann factor, where G1 is the degeneracy of this state, G0 is the degeneracy of this state. This ratio has a number 3, e to the power minus h nu by kBt, which I have written as minus T star by Ts. Okay. T star h nu by kB has a value 0.068 Kelvin, very low, and this Ts is what we call the spin temperature. So, given any number density of hydrogen in the excited state and hydrogen in the ground state, you can always determine a spin temperature. Okay. Or other way around, given the spin temperature is one way in which we quantify this ratio of the two states, the numbers of hydrogen atom in these. Okay. And when the CMBR passes through the hydrogen to us and arrives to us, so the CMBR is going through the hydrogen and coming to us, that is the picture we have. When this happens, the quantity which is important is this, the spin temperature and the CMB temperature. These are the two quantities which are important. Okay. If the spin temperature is below the CMB temperature, there will be an absorption. If the spin temperature is more than the CMB temperature, there will be emission. This is essentially in a nutshell what happens. Okay. So, the CMBR photons are coming to us through this hydrogen, and what happens in between depends on these two things, the CMB temperature and the spin temperature. The spin temperature essentially quantifies the ratio of these two, the number of particles in the excited state, number of particles in the ground state. Okay. And what decides the spin temperature? There are three processes which decide the spin temperature. So, the spin temperature basically is the number of particles, number of hydrogen atoms in the excited state and the ground state. So, transitions between these two states can be brought about by the CMBR photons themselves. So, the CMBR photons, which are characterized by T gamma, can bring about this transition. And if there were hydrogen atoms in equilibrium with CMBR, then the spin temperature would be just the CMBR temperature. Collisions between hydrogen atoms can also bring about a change in the number of particles in the ground state and the excited state. So when two particles, hydrogen atoms collide, if they are both in the ground state, after the collision, one of them or both of them can go into the excited state. Okay. So collisions between hydrogen atoms can bring about a transition, a change in the state of this hyperfine, change in the hyperfine state. And if there were hydrogen atoms which were in collisional equilibrium, the spin temperature would be the kinetic temperature of the gas. There is a third process which decides the spin temperature, which can cause this hyperfine transition. This is the so-called Witherson field effect or Lyman alpha pumping. So if there are Lyman alpha photons present, ambient Lyman alpha photons present, they will excite the electronic state, not the hyperfine transition, the electronic state. So the electron, we know the hydrogen atom has different electronic states, and finally it becomes free, right? So it can excite the ground state of the electronic transition to the first. Okay. Now this can happen in a variety of ways. The ground state itself is broken into the hyperfine ground state and the excited state. So there are two states in the ground state itself, and this separation is 1420, whereas alpha transition is 1216. But this transition can take one electron from and bring the atom back to this state, or the reverse can also happen. Okay. So this interaction with Lyman alpha photons can also bring about these transitions, and the temperature here is the color temperature, okay, which is the slope of the Lyman alpha radiation at that frequency range, 12 over there. Okay. And if there were hydrogen atom where the hyperfine transitions were in equilibrium with this, then that would be the color temperature. Temperature would equal to the color temperature. And in most situations, the color temperature is basically approaches the kinetic temperature of the gas. Okay. So there are three processes which can cause these hyperfine transitions. One of them will try to take the spin temperature to the CMB temperature. Both of these in most cases will try to make the spin temperature the kinetic temperature, the motion of the hydrogen atom. Okay. These are the three processes which are at play. Okay. Right. And so in a cosmological context, as the universe expands, all three processes are at play, right? And you have this CMB photons, you have kind of collisions between atoms, you have the Lyman alpha photons also possibly, and this equation tells you what the spin temperature will be when you have a combination of all three. These are the coupling coefficients, the collisional coupling coefficient and the Lyman alpha Witherson field coupling coefficient. This depends on the electron density and the temperature. This depends on the ambient Lyman alpha photon density. Okay. And sorry, up, it seems to jump. Okay. Now what is it that we observe? Let me also tell you this. So you see, if there was no hydrogen in between, the CMBR photons would be observed at T gamma over here. But because of the interaction with the hydrogen, the temperature of this radiation which you receive, the brightness temperature, is now different from T gamma. And what you observe is the excess, that is the temperature, that is the brightness temperature of the radiation that you actually receive minus the photon, the CMB the background CMB temperature if this hydrogen were not there. Okay, this is the brightness, excess brightness temperature, and this is what we observe, and this will vary with direction n and frequency nu. Frequency nu corresponds to a distance, direction n is this, some direction. Okay. And this formula here allows you to calculate the fluctuations in the brightness temperature. This term arises because of fluctuations in the density of the hydrogen and also peculiar velocities. Okay, and it has this factor 1 minus T gamma by Ts, where T gamma is the CMB temperature and Ts is the spin temperature. Okay, and there is this factor here which arises due to spin temperature fluctuation. So these are the two things which contribute to brightness temperature fluctuation. Oops. Okay. In a nutshell, what happens is as follows. Okay, and if you fix the frequency and direction, so direction here and frequency tells you the distance, so you have to look at these quantities at some point here, right? If you fix the direction and distance, a different direction and different frequency would be a different point. So basically, you have a three-dimensional picture of the hydrogen of something here, of the hydrogen distribution, the spin temperature, everything in this region of space. Okay, if you can measure these brightness temperature fluctuations as a function of frequency and direction, you will get a three-dimensional picture of these quantities in space. Okay, in a nutshell, again, sorry, this seems to jump a little bit. Oops. Okay, in a nutshell, what happens is as follows. If it is this term which is important, okay, in a nutshell, this is what is important. And if the CMB temperature is less than the spin temperature, then this term, the CMB temperature is less than the CMB temperature is less than the spin temperature, then this term will be positive and you will see the brightness temperature in emission, right? Spin temperature is less, the spin temperature is more, the CMB temperature is less. You will see positive brightness temperature fluctuations, you will see the hydrogen in emission. Whereas if the spin temperature is below the CMB temperature, you will see absorption. Okay, this whole thing will be negative. And there will be fluctuations which are proportional to the amount of hydrogen over there. This is the basic thing. And where will these fluctuations occur? These fluctuations will occur in this part of the CMB spectrum, very low frequency part, which is not shown here, not measured here at all. Okay, very low frequency part, meter wavelengths. Okay, this is where these fluctuations will be seen, this part of the spectrum. Okay, with this background, let me now briefly discuss our idea of the neutral hydrogen evolution. So, just after the universe became neutral, the hydrogen in the universe became neutral, there were no sources of radiation there. Okay, there is only hydrogen and the CMBR. There are no sources of radiation, no luminous sources, and this is called the dark age of the universe. Okay, and here the CMBR will be seen, the 21 centimeter line will be seen in absorption against the CMBR, like this. Okay. So there is a redshift range over here. So initially the spin temperature follows the CMB temperature, gas temperature also follows the CMB temperature. Then the gas temperature falls faster and the spin temperature is coupled to the gas temperature through collisions. But as the universe expands, the density of electron falls and the collisions are no longer able to make the spin temperature follow it. So the CMB takes over and the spin temperature is equal to the CMB temperature. Okay, so there is a range of redshifts here where the hydrogen, the 21 centimeter hydrogen will appear in absorption against CMBR. So you will see fluctuations in the radiation coming in this frequency range from this in the corresponding in this frequency range, and they will be seen in absorption. They will be negative against the CMBR. Okay. Now, after this, at a redshift of around 30 to a redshift around 6, you have something very interesting, and this is called the cosmic dawn and the epoch of reionization, this stage in the evolution of the universe. Let me spend a little time discussing this, what happens here. And to put it in perspective, let me first introduce this. So, if you look at the cosmic microwave background radiation, this originated at a redshift of 1000. And this gives you an idea of the universe at a redshift of 1000. If you look at this, you will find that it is nearly uniform. There are tiny fluctuations over there. Okay. Whereas if you look at the nearby universe, you will see that there are galaxies. And these galaxies have a clustering pattern that looks like this. This is one galaxy, and each point here is a galaxy. So you can see that this is the clustering pattern of galaxies. So there are large fluctuations over here in the matter density of the universe. Question is that you had a nearly smooth universe at a redshift of 1000, whereas now you have a very clumpy universe. How did the universe go from here to here? And we believe that this is the process of gravitational instability. These tiny fluctuations, they grow. So where there is excess, it will attract more matter from elsewhere. Where there is an underdensity, matter will flow out, and dark matter dominates the dynamics of this process. And the way this process works is as follows. You form small structures first. These small structures merge to form bigger structures, which merge to form even bigger structures. This picture is what is called hierarchical clustering. And these you may think of as halos, bound objects, dark matter halos. Okay. And this is the process by which structure formation occurs in the universe. Okay. So up to a redshift of 30, this process was going on, but there were no luminous sources. Okay. There were dark matter fluctuations. Now, at a redshift of around 30, the first luminous objects form. So you have dark matter halos which were forming. By a redshift of 30, they can accrete enough baryons, and the first stars and black holes are formed. And what first galaxies are formed. And at around a redshift of 30, so what happens? These emit X-rays which heat the intergalactic medium, the hydrogen that fills the universe, and they also emit Lyman alpha photons which couple the spin temperature to the kinetic temperature. So at a redshift of around 20, here at a redshift of around 25 or maybe larger, as I told you earlier that the spin temperature, so this line shows you the spin temperature. Spin temperature follows the CMB temperature. This line is the CMB temperature. So the spin temperature follows the CMB temperature. You don't see anything if the two are equal. The hydrogen is not visible against the CMB. The temperatures are the same. Then what happens? There are two things, and the gas temperature is somewhere here, much cooler. The gas has cooled down. What happens? There are these sources which come into the picture, and they do two things. They heat the gas. So these are two pictures of heating the gas. Okay. They heat the gas, so the gas gets heated up, and they also couple the spin temperature to the kinetic temperature of the gas. So the gas is cooler than the CMB for some time, and the spin temperature gets coupled to this. So you can see it in absorption for some time, after which again the gas temperature itself rises, so it gets above the CMB. So there is some very complex physics going on there. I have tried to give you a picture. Sorry, I forgot to give the reference to this. But I think there will be detailed talks on this in this workshop by Girish and others. So I will just speak briefly on this. So the universe also gets reionized. So in the early phases, which is cosmic dawn, there is a brief window when the hydrogen is seen in absorption, after which it goes into emission. Okay. Now, these first objects also emit photons which can ionize the hydrogen. Okay. And so these first luminous objects, they can also ionize the hydrogen, and within the redshift range 15 to 6 roughly, so this starts even earlier, but it is important in the range 15 to 6. What happens? There is ionizing radiation which come out of these first luminous galaxies, and this a part of this, so the radiation, the ionizing radiation has to have energy more than 13.6 electron volts. So this starts ionizing the hydrogen, and these ionized bubbles form around the first galaxies, and these bubbles grow and they overlap, and then the whole universe is ionized by a redshift of 6. So let me show you a video of this. So this shows you the halos, where the first galaxies are being formed, and this is the ionized sphere which is being formed by the radiation coming out of these halos. And you can see that these grow, the halos also, number of halos also increase, and the ionized regions grow, and slowly the whole universe is ionized. Okay. So this is a transition from a situation where the entire universe is filled with neutral hydrogen to, to a situation where you can see that it is completely ionized. Okay. Once the universe is completely ionized, we have what is called the post-reionization era. So you can see that the diffuse medium, there is no diffuse hydrogen here, but there are these small things which I have shown here. These are high dense, over dense regions where the hydrogen has survived the ionization. We know that they exist because we can see them in absorption against quasar spectra. Okay. And this picture shows you the amount of hydrogen we believe that there is. Okay. So in the redshift range 1 to 6, even 0 to 6, there is hydrogen in this protogalaxies, galaxies, small clouds. Okay. And if you look at that at a coarse grain, you will see something like this. These are all individual galaxies which host hydrogen in them. It is not diffuse hydrogen. And with the passage of time, the clustering of these sources, the galaxies, increases, and you can see all of this in the 21 centimeter radiation in emission. Okay, these structures get more and more prominent with the passage of time. Okay, so you can see the filaments, the cosmic web, all kinds of things here. Right. So in the post-reionization era, you do have some hydrogen still left. They are in these compact objects, and you can see the collective emission from these sources, and this is seen in emission. Okay, this is the post-reionization era. Okay. Now what do we observe? So I have, in the past few slides, I have tried to give you a picture of the cosmic evolution of neutral hydrogen. It started at 1000 and it ends at present, more or less. In between, we had this transition where the whole universe became ionized. So one kind of observation is the global signal. So you can take a telescope, radio receiver, and look at the average over the entire sky. Okay. This is called the global signal. So you look at the average. So it is just a function of frequency or redshift. And there have been maybe more, but I have put the pictures of 2 instruments here. I will not talk about this in any detail beyond this slide. Okay. So this is what is called the global signal. You average over all directions in the sky and just look at the radiation as a function of frequency. Okay. What I will speak about next, spend a little time speaking about next, is this. So I am going to talk about fluctuations, right. So you have hydrogen in space which is producing some effect on the CMB, on the radiation that you receive, and the brightness temperature of that radiation is is going to be different along different directions, and it is also going to be different along frequency. Frequency corresponds to the third dimension, depth, and 2 dimensions are the 2 dimensions on the sky. Okay. So, what we are going to observe is that the 21 centimeter brightness temperature fluctuates with both frequency and direction on the sky. Okay. We have a 3-dimensional view, and what we do is that we take the Fourier transform, look at these fluctuations as a function of the k vector, take a Fourier transform of the wave number, and look at this quantity, which is essentially the amplitude squared of these fluctuations in Fourier space divided by the volume under observation. This is what we call the power spectrum. Okay. This is the quantity which is of primary interest. You shall hear about it quite a lot in the workshop. So, I thought it would be good to at least define it once. So, you basically take the Fourier transform of these fluctuations in space and look at the modular square of the amplitude of these fluctuations as a function of the comoving wave number of the wave number. Okay. This is the quantity of interest. So, I have just shown one picture of what kind of power spectrum we expect to see in units of these units here, millikelvin square megaparsec. Okay. Just to put it in perspective, this is a rather old picture, but anyway, it is a picture of the dark matter power spectrum, which has been measured by a variety of observations, and 21 centimeter observations also will contribute to such a picture of the dark matter power spectrum. Okay. Right. And if you can measure, just to give you an example, in the post-reionization era, the power spectrum will essentially trace out the dark matter power spectrum. You can then hope to measure the baryon acoustic oscillations, the signature of the neutrinos, and also maybe through the growth factor, the redshift space distortion can give you a picture of the growth factor, which you can use to test theories of gravity. Okay. Just to talk briefly about some of the work which we are doing, well, I am going to talk about some of the work which we did maybe 2 decades, 20 years ago. So, this is where we started. Our first paper in this field in 2001, and our work was largely motivated by the giant meter wave radio telescope, which at that time was under construction, and there are several other telescopes which have come up since then, the LOFAR, MWA, right, and some of them whose pictures are not here also. SKA is what will come up, right, and HERA I have not put here. Okay. Now, this is a picture of the galaxy of the sky as measured by this Haslam. This is so called Haslam map, okay, at 408 megahertz all sky map. And we also carried out some observations, just to tell you about some of the things which we have been doing. So, we observed this particular small part of the sky, which is kind of the field of view of the GMRT on this scale. Okay. And this is the picture of the observations which we had done 2008, and what you see here are point sources, are radio sources in that particular field which we had observed. Okay. And this is a measure of the brightness temperature fluctuations in that field and in several other fields. Just to put things in perspective, I just look at the number here, 10 to the power 4 millikelvin square, whereas the fluctuations which we are talking about, the 21 centimeter signals, it is of the order of 10 to the power minus 3 minus 4 millikelvin square, right. So, the point is that what we measure, just take a simple radiometer and make a radio interferometer and make a measurement of the fluctuations which you receive, you will find that it is something else that dominates the signal, and these are foregrounds. So, what are, oops, right, these are foregrounds, and this is one of the fields which we had observed, and what we measured here is actually the brightness temperature fluctuation of the diffuse galactic synchrotron emission. Okay. But the point is that the sky, the radio sky is filled with various other things which are not the 21 centimeter radiation which we are trying to measure, And on small angular scales, you have these point sources, radio sources, which fill the sky, discrete radio sources. On large angular scales, you have the diffuse background galactic synchrotron radiation, and removing these foregrounds is possibly the biggest challenge in this field to measure the 21 centimeter signal. Okay. So let me just quickly summarize what I talked about. The CMB observations give us a picture of the universe at a redshift 1000 when the radiation and the matter parted ways for the first time. The galaxy surveys give us a picture of the universe at low redshifts like the one here. 21 centimeter observations hold the potential of allowing us to probe this entire history of the universe. Entire history of the universe. Okay. And this is my summary. So, redshift at 21 centimeter radiation fluctuates with frequency and angle in the sky. These can be used to do a variety of studies at very high redshifts, around 50, the dark ages. This is possibly the only way you can study the dark ages. You can probe the primordial power spectrum, address the question if the primordial power spectrum has some non-Gaussianity or not. At lower redshifts, you can probe cosmic dawn, the formation of the first luminous objects, how the universe got reionized. And even lower redshifts, after the universe was reionized, the fluctuations essentially trace the dark matter. So you can ask questions about the baryon acoustic oscillations, which can give you a handle on dark energy. The growth of fluctuations, which can give you a handle on the theories of dark matter. You can look at galaxy formation, cosmic web. Foregrounds are the biggest challenge in this field. Okay, thank you. Oops. Thank you for your attention.
Yeah, thanks, Somnath. Do we have any questions? Somnath, if I could ask one, I was wondering if you could comment on the usefulness of statistics other than the power spectrum. Is this just a relic of our work on CMB that we are discussing power spectrum? Perhaps it's the least useful statistics in this field.
Well, power spectrum is the simplest statistics that you can think of, because if you have fluctuations, it is essentially the variance. The mean is 0. You have fluctuations around the mean 0, right? Or the mean is what the global signal is measuring, right? We are interested in the fluctuations in the brightness temperature. So the mean is 0, and the power spectrum is the variance. So you could have different measures of the variance. You could look at the variance as a function of length scale if you smooth it, but power spectrum is possibly the best measure of the variance. So that way it is a useful statistics. There are other statistics which you can look at. We have also looked at them. For example, the bispectrum, which is a higher order statistics, which will be there if the field is non-Gaussian. And you can also have statistics which deal with topological features. So you can look at the shapes of the ionized region. Are they spherical or are they elongated, right? And various such things. So there are other statistics also, and which we have also looked at, which have been other people have also looked at. Okay, I have not talked about them here.
No, thank you. Any more questions? We have a couple. Yeah, there is a question there.
Yeah, there are three factors as I mentioned. So there are essentially three factors. There are fluctuations in the number density of hydrogen, right? Some place there will be more, some place there will be less. That being more or less could be again due to two reasons. Well, maybe the density itself is low and density of hydrogen itself is higher, or maybe it is ionized and not ionized, right? So this is one thing. There are peculiar velocities, so the hydrogen could be moving, and the motions in the hydrogen also appear as density enhancements basically. in the way we observe. And there can be spin temperature fluctuations, these three things. It was there in that equation, one of the equations. Turbulence, okay. Turbulence does come into the picture. The intergalactic medium is turbulent, definitely. But what we are talking about are not turbulent flows. In much of what we have talked about, they are coherent flows into or out of overdense and underdense regions. Okay, but turbulence is there definitely on large scale. These are all very highly turbulent. They can be highly. I mean, the Reynolds numbers are extremely large.
Right. So another thing, I have one of your schematic you have shown that merging dark matter formation.
Right.
Is
dark matter halo.
Halos.
Yeah.
So it's kind of a inverse cascading kind of a thing is happening. Is it so?
Yeah. Well, it is like that in a sense that. But this is not. I mean, see, when you speak of inverse cascade or cascade, that has to do with the geometry and the dynamics, right? I mean, I presume you're from the turbulence background. Yeah, fluid mechanics, right? So, so this is slightly different in the sense that whether the cascade will be from small to large or large to small, that is your question, I presume.
Inverse cascading.
Right.
I mean, from small to large.
Small to large. Right.
I mean,
that is right. Yeah. That is here decided by the slope of the initial power spectrum.
Right,
you see.
Right.
So when the universe was, I mean, there was some process which gave some initial spectrum of fluctuations, and here the gravitational instability. Basically, then everything grows. Okay, and it has to do with the slope of that. Right. So it is a little different from what happens in there. You have a transfer of energy from one scale to another, which decides the cascade. It is something different. Okay, but that, I mean, just in case you are interested, this 21 centimeter observations can also be used to probe turbulence. Right, but that is a different game. Okay, so if you are interested, you can speak to Nirupam or Proshun. They are here. So it can be used to probe turbulence also, but I don't think that will be spoken about in this workshop. Okay, so for example, these galaxies, the interstellar medium of galaxies is turbulent. Okay, and that can be probed. That has been probed actually. There are papers which I am also a co-author, where we have studied the turbulence in the interstellar medium.
Can you measure the Reynolds number or the intensity?
They are very large. Okay, the Reynolds numbers I think are extremely large, tens of thousands or hundreds of thousands, something like that.
Okay. On that note, let's thank Somnath again.
Thank you.